Lattice Boltzmann methods, is a class of computational fluid dynamics methods for fluid simulation. Instead of solving the Navier-Stokes equations, the discrete Boltzmann equation is solved to simulate the flow of a Newtonian fluid with collision models such as Bhatnagar-Gross-Krook. By simulating streaming and collision processes across a limited number of particles, the intrinsic particle interactions evince a microcosm of viscous flow behavior applicable across the greater mass. Algorithm, LBM is a relatively new simulation technique for complex fluid systems and has attracted interest from researchers in computational physics. Unlike the traditional CFD methods, which solve the conservation equations of macroscopic properties numerically, LBM models the fluid consisting of fictive particles, and such particles perform consecutive propagation and collision processes over a discrete lattice mesh. Due to its particulate nature and local dynamics, LBM has several advantages over other conventional CFD methods, especially in dealing with complex boundaries, incorporating microscopic interactions, and parallelization of the algorithm. A different interpretation of the lattice Boltzmann equation is that of a discrete velocity Boltzmann equation. The numerical methods of solution of the system of partial differential equations then gives rise to a discrete map, which can be interpreted as the propagation and collision of fictitious particles. In the computer algorithm, the collision and streaming step are defined as follows: collision step, streaming step. Here are the directions of momentum. Development from the LGA method. LBM originated from the Lattice Gas Automata method, which can be considered as a simplified fictitious molecular dynamics model in which space, time, and particle velocities are all discrete. For example, in the two-dimensional FHP model, each lattice node is connected to its neighbors by 6 lattice velocities on a triangular lattice. There can be either 0 or 1 particles at a lattice node moving with a given lattice velocity. After a time interval, each particle will move to the neighboring node in its direction. This process is called the propagation or streaming step. When more than one particle arrives at the same node from different directions, they collide and change their velocities according to a set of collision rules. Streaming steps and collision steps alternate. Suitable collision rules should conserve the particle number, momentum, and energy before and after the collision. LGA suffer from several innate defects for use in hydrodynamic simulations: lack of Galilean invariance for fast flows, statistical noise, and poor Reynolds number scaling with lattice size. LGA are, however, well suited to simplify and extend the reach of reaction diffusion and molecular dynamics models. The main motivation for the transition from LGA to LBM was the desire to remove the statistical noise by replacing the Boolean particle number in a lattice direction with its ensemble average, the so-called density distribution function. Accompanying this replacement, the discrete collision rule is also replaced by a continuous function known as the collision operator. In the LBM development, an important simplification is to approximate the collision operator with the Bhatnagar-Gross-Krook relaxation term. This lattice BGK model makes simulations more efficient and allows flexibility of the transport coefficients. On the other hand, it has been shown that the LBM scheme can also be considered as a special discretized form of the continuous Boltzmann equation. From Chapman and Skog theory, one can recover the governing continuity and Navier-Stokes equations from the LBM algorithm. In addition, the pressure field is also directly available from the density distributions, and hence there is no extra Poisson equation to be solved as in traditional CFD methods. Lattices and the DNQM classification. Lattice Boltzmann models can be operated on a number of different lattices, both cubic and triangular, and with or without rest particles in the discrete distribution function. A popular way of classifying the different methods by lattice is the DNQM scheme. Here dn stands for n dimensions while qm stands for m speeds. For example, D3Q15 is a 3-dimensional lattice Boltzmann model on a cubic grid, with rest particles present. Each node has a crystal shape, and can deliver particles to each of the 6 neighboring nodes which share a surface, the 8 neighboring nodes sharing a corner, and itself. real quantities as space and time need to be converted to lattice units prior to simulation. Non-dimensional quantities as the Reynolds number remain the same. Lattice units conversion, in most lattice Boltzmann simulations, is the basic unit for lattice spacing, so if the domain of length has lattice units along its entire length, the space unit is simply defined as. Speeds in lattice Boltzmann simulations are typically given in terms of the speed of sound. The discrete time unit can therefore be given as, where the denominator is the physical speed of sound. For small-scale flows, operating with the true speed of sound can lead to unacceptably short time steps. It is therefore common to raise the lattice Mach number to something much larger than the real Mach number, and compensating for this by raising the viscosity as well in order to preserve the Reynolds number. Simulation of mixtures. Simulating multiphase multi-component flows has always been a challenge to conventional CFD because of the moving and deformable interfaces. More fundamentally, the interfaces between different phases or components originate from the specific interactions among fluid molecules. Therefore it is difficult to implement such microscopic interactions into the macroscopic Navier-Stokes equation. However, in LBM, the particulate kinetics provides a relatively easy and consistent way to incorporate the underlying microscopic interactions by modifying the collision operator. Several LBM multiphase multi-component models have been developed. Here phase separations are generated automatically from the particle dynamics and no special treatment is needed to manipulate the interfaces as in traditional CFD methods. Successful applications of multiphase multi-component LBM models can be found in various complex fluid systems, including interface instability, bubble droplet dynamics, wetting on solid surfaces, interfacial slip, and droplet electrohydrodynamic deformations. Thermal Lattice Boltzmann method. Currently, a thermal lattice Boltzmann method falls into one of three categories: the multi-speed approach, the passive scalar approach, and the thermal energy distribution. Limitations. Despite the increasing popularity of LBM and simulating complex fluid systems, this novel approach has some limitations. At present, high Mach number flows in aerodynamics are still difficult for LBM, and a consistent thermohydrodynamic scheme is absent. However, as with Navier-Stokes-based CFD, LBM methods have been successfully coupled to thermal-specific solutions to enable heat transfer simulation capability. For multiphase multi-component models, the interface thickness is usually large and the density ratio across the interface is small when compared with real fluids. Recently this problem has been resolved by Yuan and Schaefer, who improved on models by Shun and Chen, Swift, and He, Chen, and Zhang. They were able to reach density ratios of 1001 by simply changing the equation of state. Nevertheless, the wide applications and fast advancements of this method during the past 20 years have proven its potential in computational physics, including microfluidics. LBM demonstrates promising results in the area of high Knudsen number flows. Derivation of Navier-Stokes equation from discrete LBE, starting with the discrete lattice Boltzmann equation. We first do an order-Taylor series expansion about the left side of the LBE. This is chosen over a simpler order-Taylor expansion as the discrete LBE cannot be recovered. When doing the order-Taylor series expansion, the zero derivative term and the first term on the right will cancel, leaving only the first and second derivative terms of the Taylor expansion and the collision operator. For simplicity, write as. The slightly simplified Taylor series expansion is then as follows, where colon is the colon product between dyads. By expanding the particle distribution function into equilibrium and non-equilibrium components and using the Chapman and Skog expansion where is the Knudsen number, the Taylor expanded LBE can be decomposed into different magnitudes of order for the Knudsen number in order to obtain the proper continuum equations. The equilibrium and non-equilibrium distributions satisfy the following relations to their macroscopic variables. These will be used later once the particle distributions are in the correct form in order to scale from the particle to macroscopic level. The Chapman and Skog expansion is then. By substituting the expanded equilibrium and non-equilibrium into the Taylor expansion and separating into different orders of the continuum equations are nearly derived. For order. Then, the second equation can be simplified with some algebra and the first equation into the following. Applying the relations between the particle distribution functions and the macroscopic properties from above, the mass and momentum equations are achieved. The momentum flux tensor has the following form then. Where is shorthand for the square of the sum of all the components of and the equilibrium particle distribution with second order in order to be comparable to the Navier-Stokes equation is. The equilibrium distribution is only valid for small velocities or small Mach numbers. Inserting the equilibrium distribution back into the flux tensor leads to. Finally, the Navier-Stokes equation is recovered under the assumption that density variation is small. This derivation follows the work of Chen and Doolan. Mathematical equations for simulations. The continuous Boltzmann equation is an evolution equation for a single particle probability distribution function and the internal energy density distribution function are each respectively. Where is related to by. Is an external force, is a collision integral, and is the microscopic velocity. The external force is related to temperature external force by the relation below. A typical test for one's model is the Rayleigh-Bar Copyright-Nard convection for macroscopic variables such as density, velocity, and temperature can be calculated as the moments of the density distribution function. The lattice Boltzmann method discretizes this equation by limiting space to a lattice in the velocity space to a discrete set of microscopic velocities. The microscopic velocities in D2Q9, D3Q15, and D3Q19 for example are given as the single-phase discretized Boltzmann equation for mass density and internal energy density are. The collision operator is often approximated by a BGK collision operator under the condition it also satisfies the conservation laws. In the collision operator, is the discrete, equilibrium particle probability distribution function. In D2Q9 and D3Q19, it is shown below for an incompressible flowing continuous and discrete form where d, r, and t are the dimension, universal gas constant, and absolute temperature respectively. The partial derivation for the continuous to discrete form is provided through a simple derivation to second-order accuracy. Letting yields the final result. As much work has already been done on a single-component flow, the following TLBM will be discussed. The multi-component multiphase TLBM is also more intriguing and useful than simply one component. To be in line with current research, define the set of all components of the system with elements. The relaxation parameter is related to the kinematic viscosity by the following relationship. The moments of the give the local conserved quantities. The density is given by. And the weighted average velocity, and the local momentum are given by. In the above equation for the equilibrium velocity, the term is the interaction force between a component and the other components. It is still the subject of much discussion as it is typically a tuning parameter that determines how fluid-fluid, fluid-gas, and etc. interact. Frank A. L. list current models for this force term. The commonly used derivations are Gunn-Stenson chromodynamic model, Swift's free energy-based approach for both liquid-vapor systems and binary fluids, his intermolecular interaction-based model, the Inamuro approach, and the Lee and Lin approach. The following is the general description for as given by several authors. Is the effective mass and as Green's function representing the interparticle interaction with as the neighboring site. Satisfying and where represents repulsive forces. For D2Q9 and D3Q19, this leads to the effective mass as proposed by Shun and Chen uses the following effective mass for a single component, multiphase system. The equation of state is also given under the condition of a single component and multiphase. So far, it appears that and are free constants to tune but once plugged into the system's equation of state, EOS, they must satisfy the thermodynamic relationships at the critical point such that and for the EOS, is 3.0 for D2Q9 and D3Q19 while it equals 10.0 for D3Q15. It was later shown by Yuan and Schaefer that the effective mass density needs to be changed to simulate multiphase flow more accurately. They compared the Shan and Chen, Canau and Starling, van der Waals, Riedlicher-Kwong, Riedlicher-Kwong-Sove, and Penga-Robinson EOS. Their results revealed that the SCEOS was insufficient and that Car-S, Par-R, Ra-K, and RKS-EOS are all more accurate in modeling multiphase flow of a single component. For the popular isothermal lattice Boltzmann methods, these are the only conserved quantities. Thermal models also conserve energy and therefore have an additional conserved quantity. Software, open source/free software, takes a LBM, open source lattice Boltzmann code from Los Alamos Natal Lab, Parallel, F90, multi-component 2D and 3D, LIMS, open source code in 2D based on Gauss-Hermite quadrature, Parallel, Fortran 90, OpenLB, open source library based on LBM, Parallel, C++, Palabos, open source parallel C++ code with a large spectrum of lattice Boltzmann models, including thermal, multiphase, free surface, and embedded particles. Sailfish, open source LBM code for graphics processing units, with support for distributed multi-GPU simulations and various lattice Boltzmann models, LBM, free CFD code which uses LBM, J-lattice Boltzmann, interactive Java applet for experimenting with LBM, see examples, some simple example LBM code in C, LBM-C, open source CUDA code, freeware, LBSIM, software written in C++, freely available, commercial, labs or Lattice Boltzmann Solver is a commercial CFD code based on the Lattice Boltzmann method. It is developed within the framework of a consortium including Renault, Airbus and CS Communication A Systems. CS Communication A Systems is in charge of distributing the software. LBydra is a modular, extensible lattice Boltzmann simulation package capable of modeling laminar and turbulent flows, heat and mass transport, and multiple phase and multiple component fluids in complex and changing fluid flow 2D and 3D geometries. Parallel, C++/CUDA code. University of Minnesota. PowerFlow, commercial CFD code which uses LBM, created and distributed by EXA Corporation. FlowKit, professional support for the open source software Palabos. XFLOW, recent commercial CFD code based on LBM, released by Next Limit Technologies. Ultra Fluid X, commercial CFD code based on LBM with multi-GPU support, released by Fluidina GmbH Fluidina. Further reading, Deutsch, Andreas and Sabine Dorman. Cellular Automaton Modeling of Biological Pattern Formation. Berger Currency User Verlag. ISBN A978-0-8176-4281-5, Suxi, Samaro. The Lattice Boltzmann Equation for Fluid Dynamics and Beyond. Oxford University Press. ISBN A0-19-850398-9, Wolf Gladrow, Dieter. Lattice Gas Cellular Automata and Lattice Boltzmann Models. Springer Verlag. ISBN A978-3-540-66973-9, Swakop, Michael C. and Daniel T. Thorne, Junior Lattice Boltzmann Modeling, An Introduction for Geoscientists and Engineers. Springer. ISBN A978-3-540-27981-5, Jean Glozol. Lattice Boltzmann Methods for Shallow Water Flows. Springer. ISBN A3-540-40746-4, He, X, Chen, S, Doolan, G. A novel thermal model for the lattice Boltzmann method in incompressible limit. Academic Pressa, Guo, ZL, and Xu, C. Lattice Boltzmann method and its applications in engineering. World Scientific Publishing. Notes, Suxi, p. 68, Suxi, Appendix D, Suxi, Chapter 8.3, pages 117 to 119, McNamara, G., Garcia, A., and Alder, B., A Hydrodynamically Correct Thermal Lattice Boltzmann Model, Journal of Statistical Physics, Volume 87, No. 5, pages 1111 to 1121, 1997. Shan, X. Simulation of Rayleigh-Bénard convection using a lattice Boltzmann method, Physical Review E, Volume 55, pages 2780 to 2788, The American Physical Society, 1997. He, X, Chen, S., and Doolan, G. D., A Novel Thermal Model for the Lattice Boltzmann Method in Incompressible Limit, Journal of Computational Physics, Volume 146, pages 282 to 300, 1998. Chen, S., and Doolan, G. D., Lattice Boltzmann Method for Fluid Flows, Annual Review of Fluid Mechanics, Volume 30, pages 329 to 364, 1998. Frank, X., Almeida, G., Pear, P., Multiphase Flow in the Vascular System of Wood, From Microscopic Exploration to 3D Lattice Boltzmann Experiments, International Journal of Multiphase Flow, Volume 36, pages 599 to 607, 2010. Yuan, P., Schaefer, L., Equations of State in a Lattice Boltzmann Model, Physics of Fluids, Volume 18, 2006. Harting, J., Chin, J., Madalena, V., Coveney, P., Large-Scale Lattice Boltzmann Simulations of Complex Fluids, Advances through the Advent of Computational Grids, Philosophical Transactions of the Royal Society A, Volume 363, pages 1895 1915-2005. Yuan, P., Schaefer, L., A Thermal Lattice Boltzmann Two-Phase Flow Model and Its Application to Heat Transfer Problems Part 1. Theoretical Foundation, Journal of Fluid Engineering 142 to 150, Volume 128, 2006. Yuan, P., Schaefer, L., Equations of State in a Lattice Boltzmann Model, Physics of Fluids, Volume 18, 2006. External links, OpenLB, LBM Community Forum for discussions on research, implementation, open positions and upcoming conferences, pilabos.org, a site with various resources related to LBM, including a forum. LBM Method, Lattice Boltzmann Summary, Elangen Lattice Boltzmann Mailing List, Entropic Lattice Boltzmann Method, DSFD Mailing List, sends information about DSFD and related conferences, opportunities for doctoral, postdoctoral, faculty and industry positions for applicants who have experience with Lattice Boltzmann or other related methods. DSFD.org, website of the annual DSFD conference series where advances in theory and application of the Lattice Boltzmann method are discussed, website of the annual ICMMES conference on Lattice Boltzmann methods and their applications.